Hello students, welcome back. Let's resume our discussion in section 1. We are almost there. We defined and studied Riemann sums. And before going over to Riemann integrals, let's have a brief recap. We started with partition, and this partition gives us a lot of subintervals, xi minus xi, and subinterval width is delta xi, the difference of x coordinate. And we're going to name delta x as the biggest of those in this picture, this one, red. And then using partitions, we define Riemann sums like this and visualize like that. Basically, we are looking at the sum of the area of the rectangles. Delta xi, that's the width. And that yi star, that's the height. Yi star is selected at random, anywhere between the minimum and the maximum function value in the subinterval. But there's a bit of a problem. Minimum and maximum do not always exist. In this picture here, minimum is problematic. What if this is an empty dot? Well, in order to improve, you can use a little bit advanced idea, the infimum and supremum, which work exactly like minimum and maximum, except that they always exist, then no problem. This definition is perfect, accepted even in graduate level. Now we have perfect definition of Riemann sums, but they're a little bit too hard, so let's reduce for continuous functions, because for continuous functions, yi star can be rewritten as f of xi star for some xi star. And then consequently, the randomness of yi star can be passed on to the randomness of xi star in this interval. And this is the starting form that we are going to work on, as you saw in this kind of visualization. Remember this? Because of all kind of randomness, we get widely different pictures. If you take evenly spaced partitions, then the randomness is drastically reduced. And of course, you can eliminate randomness altogether by taking the midpoint approximation 1 or midpoint approximation 2 or left-hand side and right-hand side approximations. But in any case, why do we study arbitrary case? Because after all, this is terrible approximation. Why do we study that? The reason is because in terms of application or in terms of approximation, this is bad, so nobody uses. But in terms of theory, this is the best, because in terms of theory, we want to establish the general convergence for arbitrary case. Even the worst possible case converges to the same value. That's basically what we want to establish. And here's a visualization. Looks like this approximation is terrible, but if we increase the partition number to 200 from 20, better, 2000, or much better. So you see, if we take higher partition number, even the worst possible case is improving like this. And that's the idea we adopt to define the Riemann integral. We define it like this. The Riemann integral is defined as the limit of Riemann sums where delta x is going down to 0. Hey, what is delta x? Remember? It is the maximal partition width. The red one in this particular case. So if delta x is going down to 0, that means the maximum is going down to 0. So all the delta xi's are all going down to 0, which means all the rectangles from the visualization of Riemann sum, they're all going down to infinitesimal. They're all becoming extremely thin. And that's what this limit is. And that's how we can control the Riemann sum, even though it is humongous category with, a lot of randomness. But still, you can put everything together as a single limit expression using the maximal interval width delta x concept. It can be rewritten like this, where yi star is between the minimum and maximum, or more precisely speaking, between the infimum and supremum. Now, if this limit exists, then the limit quantity is called the Riemann integral, or the definite integral of f in that interval ab. And if the limit exists, we say the function f is Riemann integrable. It turns out that all continuous functions are Riemann integrable, so this limit exists, so the Riemann integral exists. The definite integral defined like this is called Riemann integral, but there are other definite integrals, I'm afraid. Lebesgue integral, gauge integral, there are others. If they all exist, then they all share the same value, but not all of them exist. Some of them exist, some of them doesn't. What kind of problems there? So I'm not going to use the term definite integral from this point on. I'll call it Riemann integral. More precisely speaking, it is the definite integral defined through Riemann sum like this. That's Riemann integral. But I'm going to call it Riemann integral from this point on. Okay, we talked about Riemann integrability and what is Riemann integral. All right. Let's consider an application. Here's a big one. Calculate the given limit. Believe it or not, this is a Riemann integral. Let's compare this with that. All right? Or, as a matter of fact, in this case, this is a continuous function we are talking about, so I don't need this yi star. I can rewrite like this. So this is I can write like this. Okay. And then what is delta xi? Well, in this particular case, you can see we have 1 over n, and that's going down to 0, right? And here, delta x is going down to 0. That's got to be delta x. So let's manipulate like this. And move this 1 over n like this. And instead of n going to infinity, let's rewrite it as 1 over n going down to 0. Compare these two limits. They are identical. See the difference? Or see the non-difference? 1 over n just moved here, no problem there. And I changed n going to infinity to 1 over n going down to 0. Why did I change like this? Because compare that with Riemann sum. I want delta x going down to 0. Okay, next step. Please note that 1 over n is delta x. So that's my delta x. And delta x is going down to 0. Okay, all right, so far so good. So that this is an Riemann integral. Okay, but what is my function? So this one here should be f of xi star. Here, index is k. I'm using k as an index, so I have to use xk star. Oh. Okay, all right. This is what I have so, oh, no, not this. Okay, this is what I have here so far. So 1 over n, which I just highlighted in red, is delta x. And that's going down to 0, right? So getting infinitesimal, that's going to dx. Is that clear? Now, the problem is this one. Function. What is my function? Let's postpone that. Now, what is this integral? Where does it go? From where to where? Look at the summation. The summation goes from k going from 1 through n, so 1 over n, and then 2 over n, and 3 over n, and so on, right? And then eventually I get n over n, which is 1. Do you see? And then 1 over n, when n is really, really large, then that's pretty close to 0, roughly speaking. Okay, maybe not b. So let's write like this. So this integral should be going from 0 to 1. Are you with me here? So summation, it's going from k going through 1 through n. So 1 over n, 2 over n, 3 over n, and so on. So 1 over n is going to be humongous, so that's 0. And n over n, that's 1. So integral from 0 to 1. So okay, that became that. Oh, we have a problem. What is my function? That's a hard part. Okay, a picture would help. Here is sine of pi x going from 0 to 1, and then the right-hand side approximation. Because you see we have xk star or xi star, not xi minus 1. Let's see, where is the visualization? Left-hand side versus right-hand side endpoint. You see, left-hand side we need I minus 1. Right-hand side is xi. That's the one. We have xk instead of xi, but that's the only difference, the change of character. This is the one I'm looking for. And of course, it's not the midpoint. It's not something that complicated. It's the right-hand side approximation, this particular Riemann sum, that is in action. Like this. In the end, therefore, this function turns out to be like this, and this one is sine of pi x. Calculating this final integral using the fundamental theorem of calculus and getting things done, that's easy. Getting this integral is the hard part. We went through all those theoretical details, starting from Riemann sum and then comparison. I hope you understood, but I have to reveal this trick. Not everybody followed. It's a difficult concept. In real analysis 1, we're going to do this again, and there it's going to be considered as medium or easier problem, but here it's super hard. So I'll give you a shortcut. It doesn't always work, but many a times it works. There you go. 1 over n becomes dx, and that's easy to understand. 1 over n is going down to 0. Delta x is going down to 0. So that's delta x and the infinitesimal version dx. And the integral becomes, the limit of summation becomes the integral. The hard part is this. K over n becomes x, and you can mechanically change all this into this integral form. That works almost all the time. Remember, 1 over n is dx, k over n is x, and the rest is integral from 0 to 1.